In the first session, in the lecture 1 and 2, we will be taking up introduction to mini hydropower and use of contour maps, because the contour maps play a pivotal role in designing and implementing mini hydropower plants, small hydropower plants anywhere in the world. So here I have put a picture from an Indian small hydropower plants just to begin with, so that you get those who have, maybe some of you have visited small hydropower plants and large hydropower plants as well. We will see why the difference between the large hydros and mini hydros, and the importance of mini hydros compared to large hydros. Here we can see, I am sure that electrical engineers and other engineers are familiar with the typical components, which we are going to see in detail later. We can see in this power plant the penstock, and the penstock is supported by and held by anchors, etc., concrete anchors we can see, and the power plant we can also see. And then the tail race water, that is after water goes through the turbine, goes back to the river, we can see. And the electrical components little bit we can see from this picture. The overhead transmission line we can see here, and also the grid we can see, where the voltage is stepped up from the generating voltage to the transmission voltages. So, we will go through part by part of many of these components from a hydropower plant developer's view, because a hydropower plant is a multidisciplinary project, because a hydropower plant comprises of many kinds of engineering solutions. For example, a lot of civil engineering is involved and a lot of mechanical engineering is involved. For example, penstock is a mechanical engineering involvement, and the turbine is a mechanical engineering main item, and there are many. And then the electrical engineers have to play a pivotal role there, because it is electricity generation. There is electricity generators, and then the control equipment, control systems, and then the SCADAs, and then various other devices controlling the electricity flowing from the generators to the network, which is coming in a river. So, their estimations are required, where you have to judge how much electricity you can generate momentarily, as well as how much energy you can generate throughout a year, which you can sell as a commercial item to a electricity grid and earn returns for the investment. So, all these things are there. So, the hydropower engineer really has to coordinate all these things. So, in this course we are developing necessary skills for a hydropower engineer. So, therefore, we will neither try to become a civil engineer, no an electrical engineer, no mechanical engineer, but we will try to have a combined impact, combination of knowledge from a hydropower engineer, how a hydropower power plant should be planned and implemented. And for each subsection, he will use, for example, to design and construct the powerhouse, he will assign the necessary sizes to a civil engineer, who will design the powerhouse depending upon the local conditions, soil conditions, etc. And similarly, he will design, hydropower engineer will design what should be the penstock diameter and the thicknesses at different levels, and then he will ask the mechanical engineer to do the final design as to how to weld the pipes between pieces and so on. So, he will use expert mechanical engineer for that, but the hydropower engineer will do the sizing of components and the lengths, etc., and the location of the various components. All these things the hydropower engineer will do. So, in this GN course, we are looking from a hydropower engineer's point as to how to plan and develop and implement a hydropower plant, especially a small hydropower plants. So, I have done my research to find out the hydropower situation, especially small hydropower situation in India, how it stands today. So, as per the Ministry of Power, number of identified locations of small hydropower, 7,000 plus sites they have identified, and they have estimated they can generate about 21,000 megawatts, sorry 21,000 megawatts, that is a pretty big, 21 gigawatts of electricity from these 7,000 plants. And by 2020, only 1,100 plants have been developed throughout the country. Therefore, there are plenty of other opportunities where small hydropower plants can be implemented in India, and the total capacity developed by 2020 is mere 4.7 gigawatt or 4700 megawatts out of 21,000 megawatts. So, there are a large number of small hydropower potential sites available throughout the country which can be developed, and in my experience I know throughout the world that all these power plants are very much commercially viable. Therefore, there have no need for the government subsidies and also government funding. They can be developed by private sector investments. Therefore, funding requirements are not an issue. So, they are commercially viable, producing cheap electricity and sustainable electricity. And there is a confusion about this different names used in hydropower industry, small hydropower industry. I am sure you have heard about words like micro hydro, mini hydro, and sometimes for a smaller units pico hydro, and recently starting from recently the word small hydro. So, some classifications used in India, up to 5 kilowatt projects are sometimes classified as pico hydro, and up to 100 kilowatt from 5 kilowatt micro hydro, and 100 to about 2000 kilowatts mini hydro, and up to about 25,000 kilowatts small hydro. But there are no hard and fast rules about this. There are no standards, IEC standards or BS standards saying this is the classification. So, it is a country dependent classification. For example, in USA where they have very large hydropower plants, they call up to 100 megawatt small hydropower plants, and China 50 megawatt up to 50 megawatt they call small hydropower plants, and in Sri Lanka we call up to 10 megawatt or 10,000 kilowatt as small hydropower. So, this is the Indian classification, but of course, there are no hard and fast rules. So, I prefer to use small hydro for the entire cross section here. So, up to from 0 to say 25 megawatt in Indian context we can call small hydropower. So, we are discussing on this topic. So, I will be using small hydropower term small hydropower for the entire cross section of these projects less than 25 megawatt. In Sri Lanka we call up to 10 megawatt as small hydropower, and here is how the potential sites are spread across different states. We can see some states are very lucky, they have many opportunities. For example, Himachal Pradesh, the capacity estimated capacity is 3,400 megawatts, and out of that only about 1000 megawatts are constructed and under construction. So, a lot of opportunities, and similarly other, and I have had some opportunities in doing some research and helping some friends in Kerala for the development of small hydros and identifying sites some time back, and I will show you a picture where we visited some sites. So, they are also they have many opportunities. So, you can see there are large number of opportunities for the future. For example, if you take Sri Lanka, we have developed most of the mini hydro opportunities. So, there are no more commercially viable practically implementable small hydropower opportunities in Sri Lanka. There are few, but the picking up is very slow because of the various other reasons, like you have to relocate families etc., when you are doing it in townships etc., but when you are doing them in very remote areas, those problems do not exist. But in Indian context, these things are in remote areas, I believe, and therefore, they can be easily implementable. And we can also notice here that these projects are not large. For example, if you take Rajasthan, right, there are 64 projects having a capacity of 51 megawatts, right. So, that shows that each project on average is about 1 megawatt or less, right. They are small projects, not very big projects, right. So, although we earlier told up to 25 megawatt are small hydros, but most of them come into less than 10 megawatt range. If you take Kerala, for example, 238 projects, estimated capacity is 647, that is about 3 megawatt size the capacity each. There may be couple of projects having higher capacities, but on average less. Therefore, in small hydro developments, most of the projects fall into the category less than 5 megawatt capacity implemented ones. There are occasionally larger power plants as well in the South Asian context, but if you take China or USA, maybe the projects are much larger because their opportunities are much bigger. And here are some pictures taken during our visits in Kerala in 2004 with my 20 years younger those days, and see our team visited. He is Mr. Nair, an Indian gentleman, and we helped him to identify. He wanted to make some sites selected for his project. We helped him to do it because he was helping us in Sri Lanka in sourcing machines from India. We purchased some machines through him from a company in Delhi, and so we had some relationship. So he wanted, when he wanted to develop some projects in Kerala, we visited together with him and helped him to identify some commercially viable options for development. So it is important to know the comparative costs. If you take renewable energy, solar, wind, renewable mini hydro stand as very commercially viable projects to be implemented. So it is, as engineers, we should know roughly where the costs stand, in what range we are talking about. We know if you take a large hydropower plant, we normally say cost in US dollars per megawatt. That is, if to develop 1 megawatt, how many US dollars? So we can say in certain states like Himachal Pradesh and so on, the cost is somewhere about $1.4 million per megawatt. That is, to develop a 1 megawatt project, it will cost something like $1.4 million in these areas. But in some other states, it might be even cheaper. It might be even cheaper because they are maybe local costs are lower, labor costs are lower, and also maybe the opportunities are more easy to develop. So they are less than 5 megawatt capacity, and when it comes to between 5 and 25 megawatt, economy of scale comes up. Therefore, costs goes down further, because larger power plants, when you develop, naturally your costs go down in small hydro cases. But when it comes to large hydros, costs are much higher because there is a reservoir. Cost of the reservoir is huge. You have to have an expensive dam and a large extent of land to go underwater, and therefore, so compared to these things, I would say large hydro, they will go something like say $3 million per megawatt kind of, or even more, because there are a lot of relocating people cost, building new houses for them, and there are a lot of involvement. So therefore, large hydros have much higher, we call them specific cost, per megawatt cost, we call them specific cost, much higher specific cost, and the same are here in Indian rupees million, but the Indian rupee amount changes depending upon the exchange rate. Better to remember in dollar terms. So roughly have an idea with you. Small hydro development costs somewhere between 1 to 1.4 million rupees to develop 1 megawatt power plant. Then you can know something about how much is wind, how much is solar. So as electrical engineers or technologists, you must be able to have a comparative idea. Like a doctor knows medicine, as engineers we should know our subject area. So if somebody asks you how much will be the cost of a 1 megawatt small hydropower plant, you should be able to say it might be around 1 to 1.4 million dollars per megawatt, depending upon the location and also the specific requirements of that particular site. As we all know, hydropower has a very long history. If you take wind or solar, maybe last 20-25 years, right? Earlier there may have been pilot project of solar or wind, but no commercial projects. But if you take, ever since electricity was invented, immediately afterwards hydro turbines and generators were connected and hydropower plants were set up. So I have been to some large hydropower plants in Norway, huge size, and I visited one power plant 300 megawatt into 4 Pelton units. One Pelton unit was 300 megawatt. So I have a picture taken with the spare turbine, huge turbine. And China has not recently, about some 10-15 years back, they have commissioned almost the world's largest hydropower plant, 20,000 plus megawatt, one single plant in 3 Gorges Dam, and they are huge. So hydropower has a long history, and also it's a very much proven technology. And So, they have been a very good reliable renewable energy supplier at economical prices. Electricity from renewable energy projects are long standing, even small hydropower plants will run if implemented rightly, with the correct technology. They will run 20, 30, 40, 50 years with the same turbines, maybe a little bit of refurbishment, but they are long lasting, and you can always run for many hundreds of large hydropower plants. They have run hundreds of years. Maybe you replace the turbine after 30, 40 years, but still all the other components are good enough, and therefore they have a long life. But if you take a wind power plant, maybe 10, 15, 20 years maximum, then you have to throw out everything. And if you take solar power plants, their guarantees are only 20 years. So, after 20 years, you have the formidable question, where to throw the solar panels, where to dump them. So, but in hydropower, you do not have any such problems. So, hydropower, therefore, out of renewable basket, hydropower plants stand as the much better option. Therefore, all these power plant options available in India, more than 15,000 megawatts must be implemented, giving preference to them over solar or wind, which are not as good as mini hydro, because mini hydro has the other advantage, they have higher plant capacities, plant factors. Plant factors. Normally mini hydros have plant factors above 35, some running into 40, 45. Whereas if you take a solar power plant, plant factor will be about say 20% without tracking, with tracking maybe 25%. So, therefore, their economic life, the economic benefit returns are lower compared to small hydropower plants. So, the small hydros are as old as the large hydros, because they have implemented them everywhere possible. For example, in Europe, they have started with hydro turbines, not for electrical generation initially, but directly for grinding their crops, etc. And later on they shifted them to be connected to the generators. Right. So, in our countries like Sri Lanka, India, small hydros were first introduced in our countries by the British. Both countries have been European colonies. So, in their time when they grew tea and rubber, etc., to get electricity to their bungalows and factories, they installed mini hydropower plants, because they were mini hydros were available invariably in the tea estates and so on, where the highlands are located. And therefore, in Sri Lanka also, and India also probably, there have been very old mini hydropower plants installed by British in 1950s or even earlier. But as the grid growth to the remote areas, they abandoned the mini hydros, because grid power was more reliable and much cheaper, and they did not want to maintain mini hydros. So, they were given up. That is before 2000. But by the time year 2000, world energy prices increased to go up. Oil prices, which were conveniently below $20 a barrel before 2000, rose about $20 a barrel and went up to 30, 40, 50, 60, 70. Today it is about $70 per barrel. Therefore, the energy cost has risen significantly, and the result is now old abandoned sites as well as new sites of mini hydropower are very commercially viable at the present day electricity prices. Therefore, they are developed in Europe, in Americas, in China, in Asia, in South Asia, in our countries, because everywhere most of them are commercially viable and supplies reliable electricity to the grid operators. And so, hydropower projects fall into two main categories. They are storage schemes and run of river schemes. Storage schemes, as we all understand, we will see the slides and then go on, right. So, run of river schemes, as the name suggests, they use the water running in the river and utilize the water to operate the impart the energy to a turbine, and then directly put water back to the river. There is no water storage, water collection, and therefore, these projects are much more environmentally viable and environmentally less polluting or less interfering compared to large hydropower plants. And this small hydropower, which might be pico hydro, micro hydro, mini hydro, whatever the name suggests, 95% or even over that are run-off river power plants, No storage reservoirs are there, but there are few mini hydropower plants, as we will see in later chapters, later discussions, have been developed in existing dams, and the new dams have not been constructed, but in existing dams there have been hydropower plants developed to utilize the energy potential. So, there are about very few, maybe 3-4% number of small hydropower plants connected to reservoirs. That is not because reservoir was made for the mini hydropower plants, that is because reservoir was available, and therefore, that was utilized to create a mini hydropower plants. Otherwise, all small hydropower plants come into run-off river category. We will see what is run-off river in more details if you did not get the full idea in the later slides, where I will be discussing with some diagrams. One issue with run-off river power plants is that you can't carry water from wet season to dry season. That is the advantage of having a reservoir. You can collect water during wet season and preserve it, and then utilize that water to generate during dry season. So, that facility is not available with run-off river power plants, but that facility comes with a huge environmental impact of the large hydropower reservoir, where you keep the water collected, which has been flowing perennially over thousands of years downstream. Now, you stop everything, collect it in your reservoir and use it as you wish. So, which is a huge environmental intervention, and that ecological system, all the animals, trees, and even people who are downstream are severely affected. Therefore, in the present day context, large hydropower plants are not thought of as environmentally friendly power plants, other than the benefit of not releasing greenhouse gases. So, even large hydros have the advantage, they do not release greenhouse gases, and therefore, they are considered as environmental friendly, but the ecological impacts of large hydropower plants are sizable and presently thought of as not very environmentally sustainable. So, and another advantage of run-off river power plants are they can be built, that without much expert knowledge. You do not have a reservoir control, you do not have to build a reservoir. Therefore, they can be constructed, these power plants can be constructed with local engineering knowledge, and also they have better long term reliability. And so, they are very environmental friendly, and downstream flow patterns are not affected, and there will be no appreciable upstream flooding. When you block a river and prepare a dam and collect water, backwater level. So, if you construct a dam and collect water, right, your backwater curve, right, earlier river was flowing at this level, now you raise the water level. Therefore, the river's water level, backwater level will go up in the upstream to some maybe few kilometers, and the lands adjoining the river previously not flooded will now be flooded permanently because of the formation of the reservoir. So, all the maybe crop growing people will have maybe tea estates, rubber estates, so other farmers will be affected by the lands newly going underwater. So, that is also an environmental impact of having a reservoir connected to a large power plant. So, they are having issues. So, as I said earlier, small hydropower projects are almost always run-off river type. So, I will be using the word, as I said earlier, small hydropower projects for all the power plants starting from say 5-10 kilowatts up to say 25 megawatts in Indian context. And so, the storage schemes, right, they have a water collected on a large reservoir. So, So, the advantage is this water can be used during the the dry season when there are no rivers, no rains, but the small hydropower plants will operate only with the rainwater available. But when I say rainwater, it is not necessary to the rain to come every day, because the catchment areas where the water is falling will have certain water retention capacity. If you take a forest, when the rains come, the certain water goes under the soil, and then they will be released slowly as fountains later on. So, even if the rains are not there, there will be water available in the river for some time, and by that time again the rains will come. Therefore, there is a sustainable way of doing it, because even if the rain is not there, these small hydropower plants will still operate, of course, with some reduced capacity if the water level goes down slowly. So, the storage schemes are more complex and expensive because of the reservoir, and they will face the problem of silt accumulation. In large reservoirs, if you take the reservoir over the long term, there will be the silt accumulated in the reservoir, and the reservoir's water capacity will gradually go down. Therefore, either you have to remove silt or otherwise your water retention will be lower and lower. This is especially happening because of the lot of agricultural activities in these areas, which will let lot of silt to flow and to end up in the reservoir bottoms. So, therefore, these are negative impacts of large hydro. So, on in all we can say, large hydropower plants, although they can give a big capacity, have number of issues due to the involvement of the reservoir, and therefore, they are not thought of as environmentally sustainable, environmentally friendly projects in the present day context. Here, if you didn't get, some of you didn't get the idea of run of river power plant, here is a typical diagram which I will be referring from time to time during this course. So, this gives an idea about what are the components and how we do plan small hydropower plants. So, we can see in the blue line the natural water flow in the river. So, river flows in its natural course, right, and goes down, and there is a height difference. This is a hilly area. From this point to this point, there is a certain height difference, maybe 50 meters, 100 meters, 200 meters, 500 meters, depending upon the location. So, that is what we are going to use. We are going to use the potential energy of water at the high altitude converted to electricity. That is the purpose of a hydropower plant, whether it is a large hydropower plant or small hydropower plant. Small hydropower plant, we are using simple components compared to a large hydropower plant. So, here we have identified the height, and we have identified the location where the water can be diverted, right. So, here we have identified the location for the powerhouse, right. So, there are number of choices. You can put a penstock straight from here to here, steel pipe. Somebody might argue, okay, why not? They can do, but that is not the way that we do it. We will explain why it is so. So, we normally take water through a low pressure canal or channel to a convenient location closer to the powerhouse. So, we can make the penstock as short as possible. We will have a discussion on the penstocks later, but penstocks are expensive on one hand, because it is usually steel. Penstocks are expensive, right. Therefore, if you do it this way, it will be much longer and more expensive. And on the other hand, when the water flows through the penstock, depending upon the penstock diameter and the internal resistance, there will be internal losses. We call them head losses in technical terms. Therefore, longer penstocks have longer head losses. Therefore, the electricity amount you can generate from this penstock, long penstock, will be lower, comparatively lower by the short penstock. Therefore, we want to bring water to a convenient location on a canal, and then start the penstock from there to keep the penstock as short as possible, right. So, there are a number of terms we use for this canal or channel, right. So, we use it. You can see there are some overflow canals here, and also another one here, and then we can see there is a tank here, what we call the 4-bay tank, right, where water, why we will see later why we need the 4-bay tank, and from where the penstock will start and will be connected to the turbines here. Here we can see the turbine, and then we can see the generator here, which are coupled together and which will produce electricity, and that will be connected to the grid. So, it is a typical configuration of a layout of a small hydropower plant, which is operated on run of river basis. You can see we are using the same water. So, when we divert water, we will provide some water, major water component to the canal, but we will release some water into the river as well, what we call the environmental flow. To keep this river section from A to B, again we do not want it to be dead, right, without water. So, the environmental investigations of the project will reveal how much should be the simple queue, depending upon the nature of the project, right. Therefore, when you obtain the environmental approval from your whatever the environmental board, they will check how much water should be released from the diversion point to keep the river live. So, that the river, trees, plants, animals in that river section will not die, right. Therefore, the water which diverted will be go through the power plant and come back here. So, the affected part of the river is only A to B, that is also having without detrimentally affecting it, because we release the environmental flow. Q is called the environmental flow or the minimum flow, right, which is determined by the environmental investigations. So, therefore, this small hydropower plants are having a minimum environmental impact, right, because we want to keep even the affected river section live, So, we can see the other components of the power. So, we will be in this course, we will see how to locate this location, why not here, why not upstream, right. So, we will see some ideas on that. So, when you have to identify them, and then how many overflow canals we need, and what should be the slope of the canal, because if you use more slope, your head will be less. Therefore, typically the slope of a canal will be about 1 to 1000 typically. So, that is 1 millimeter per 1 meter length, right, 1 millimeter, that is enough just to water to flow. We want just to water to flow in the canal. It is not necessary to have any pressure or any speed, much higher speed, right. We want just water to flow and come to the 4-bay tank, come here, and from there onward water speed will pick up in the penstock and provide the necessary pressure for the turbines to operate. So, really the head will come from here, top water level to the turbine level. We will discuss these terms head and so on later. I am just indicating the sizes here as an introduction, but we will see these things in more details as we discuss in the future topics. So, in Indian context, here are some steps that if anybody is, if you are joining a company and the company wants to develop a small hydropower plant. So, these are the steps that you should follow, your company should follow for the development of project, right. So, identification or selection of the SHP site, that is something that we will discuss in this project, and then evaluation, you have to evaluate to see whether it is viable, and submission of a pre-feasibility report, right. So, to this extent the knowledge required we will be discussing in this course. So, with this knowledge you gain from this course, you should be able to prepare a pre-feasibility report in order to make an application to the whatever the authority that you should be submitting the proposal, and then obtaining the no objection certificate or clearance certificate by the developer, and submission of detailed report, grant of techno-economic clearance. We have to do some economist has to do a techno-economical viability check. So, some estimations are required, what are the benefits coming out of the project, and some estimations are required, how much will be the total cost of the project, and then you must do a cost benefit analysis and see whether it is economically viable. then signing of the implementation agreement, and most importantly signing of the power purchase agreement. Sometimes you have heard these terms PPA. As engineers, electrical engineers and engineers, we must be familiar with these terms. Every power plant is having a power purchase agreement signed between you and the utility or the utility in that area. So, a power purchase agreement will give the long term, maybe for 20 years, usually they are for 20 years. So, every hydropower plant, every solar plant, every wind power plant, every private power plant has a negotiated or standard power purchase agreement between the developer and the utility, and therefore, you must know what are these things. You can have a look at typical PP. We are not discussing about PPAs in this course, but you can download, there are sample PPAs in the net, you can get them and have a look at. But as an engineer, if you join a private company or government company, whatever, doing renewable projects, right, private investments, then you must be familiar with power purchase agreements, because invariably you will have to discuss these things with the utility, whoever the your network operator, and then discuss the terms to the advantage or the mutual advantage of developer or your company and the electricity utility that you are going to be connected to. Then the funding arrangements, you will have to talk with the bank and talk with your company, how much we can put. The bank's investment, we call it as a loan or debt, that we have to talk about loan or we call it debt. And then investors contribution, this is coming from a bank, and investors investment, what we call equity. This is the developer or your whatever the company that you have. So, usually for hydropower plants, this is about 30 to 70%, equity 30 and debt about 70%, but it can vary from 80-20, 60-40 depending upon the various other financial conditions and risks associated with the project. And then arrangement of the equipment and manpower, you have to discuss with the suppliers who can supply the best equipment for my project, and then the construction, completion and commissioning. So, these are the steps involved in a small hydropower development if you are joining a small hydropower developing company. And of course, in this course what we learn will be useful for you to do the pre-feasibility study and to see the financial viability of the project. And contour maps, right? Contour maps are very useful in understanding and designing and identifying small hydropower projects or even large hydropower projects, right. And I forgot to tell you, in large hydropower projects, this canal usually in renewable energy, small hydropower projects is the equivalent counterpart of the tunnel. I am sure in large hydros you have heard about the tunnels. So, the tunnel is the low pressure tunnel doing the same purpose, going on a very low slope, bringing water to a convenient location to make the penstock shorter. So, in a large hydropower plant, the function done by the canal in a run-off river power plant and small hydropower plant is done by a canal in large hydropower plants, a tunnel in large hydropower plants. So, understanding this canal or tunnel path, right, is facilitated by the contour maps. Contour maps will guide you how you should route, how the route of the canal, how the route of the tunnel should be designed or planned. And then contour maps can be used to identify what should be the better location for the water diversification, right, that is, using the contour map you can see where should you start this diversification, water diversion, right. So, contour maps will be helpful, and then where should be your penstock be placed, that will also be facilitated by a contour map, and where the power plant should be, because the power plant should be placed so that No, in the flood season this water level will raise due to floods. So, your power plant should not be inundated, otherwise your equipment, control equipment, generator will be going under water, and this should be then in technical terms we say it should be above the 100-year flood level, right. So, how to identify those things we will discuss in the coming topics, right. Therefore, contour maps will facilitate identify all these things. Therefore, development of small hydropower projects or even large hydro projects, contour maps play a crucial role. Therefore, we will have a brief idea here about contour maps, and then we will during our discussion we will refer to them time and again depending upon the requirement. So, you know that contour maps can be 1 to 50,000, right, in general, and maybe in detail contour maps can be even 1 to 10,000 scale, right, 1 to 10,000 scale. So, the survey departments in the region, maybe in your Indian case your state survey departments normally publish covering the entire state. These days all the areas are covered by these maps, because they have a lot of technologies now, satellite technology and so on, and therefore, they can take images, satellite images and so on. So, they have very accurate contour maps, right. So, but sometimes in some areas they may not have produced 1 to 10,000 detailed map, because they are not required. If it is a huge forest area where no development activities are taking place, probably they may not have produced 1 to 10,000 maps, because they are not required. But when the development activities are happening, these maps are really useful, right. So, a contour map shows lines of representing equal heights on the ground with the heights indicated level above the mean sea level. So, if you take a hill, right, say if it is say if the sea level is here, right, you can say, so this circle represent height above the mean sea level, say 1000 meters, right, and the next line can say 1100 meters, and next line can say 1200 meters, and next one may be 1300 meters, top may be 1400 meters. So, you can plot the contour map, and this is 1000 meters contour map, this is 1100 meters, this is 1200 meters, this is 1400 meters, and top is 1300 meters, top is 1400. So, this is the contour map of this hill, right. I just took as 100 meters difference, but survey departments normally have say from every 10 meter gap. So, if they want they can say 1000 meter, next one may be 1020 meter, and next one may be 1040 meter and so on. So, depends upon the survey department who has chosen it, but in most cases they normally go by 20 meter contour heights. So, this is the hill, this is the contour map, that is the idea. So, you can likewise you can do it to an entire region. If it is a flat area, say this is a flat area, right, contour map will be just one line, no other lines. So, it is 1000 meters, no other lines, because there are no other hilly areas, entire area is flat 1000 meters like a playground. So, when you see a flat area like this in a map, you should understand when the contour lines are there and no other contour lines, you must understand that is a flat area, right, that is a flat area. So, flat areas are not good for hydropower development, because we want for hydropower a height difference between the water availability. So, that you can use the potential energy of water to drive a turbine, right. So, if you see something like this, that is a flat area, something like this, that is a hilly area. So, this is good, This is not good for hydropower, flat areas, right. So, now we can look at a sample, okay, we will come to a sample map later, right. So, some information about sample maps, right. In addition to the contour lines with 20-meter height difference, main roads normally in red cover, by roads and cart roads normally in yellow and white color depending upon the authority. Usually these are British, even in Sri Lanka or India, I think the survey departments were first set up when the colonial rule was there. Therefore, they are usually uniform. The laws and rules and applicable in India and Sri Lanka are British originated. Therefore, these contour maps and other things are pretty uniform. So, normally they are in 20-meter height difference. You can investigate, go to your, I saw that in some of your survey departments you can freely download some contour maps up to certain accuracy. So, you can go and give your telephone number or something, mobile number, and get the authority and get download sample contour maps and see. And so, they also indicate rivers and streams, which is very important for us, because we are going to deal with the river or stream. So, every contour map has all the details of where the rivers are flowing, and usually they are colored in blue lines. We will see a sample only. And then the provincial boundaries, your state boundaries, all will be in the contour map saying this is the boundary between, say, Tamil Nadu and Odisha or whatever. The lines will be all will be marked, right. And the paddy fields, estates, tea estates, forests, all are detailed there. Then you can see from the map that these information are available, and many other information are contained in a good contour map. 50,000 scale maps are good enough for initial studies of small hydropower projects, while 1 to 10,000 maps are more useful in final designs. So, we will normally do the initial design with the 1 to 50,000 map, but after identifying the locations, maybe the canal path, maybe the forebay tank, maybe the diversion weir, we will get the 10,000, 1 to 10,000 map of that location. That will give more details. So, that will help us to do the designs better, But I have done 2 projects, small hydropower projects as the project manager. I will show you some photographs if the time permits later. And but finally, before you really do the project, you will mobilize a survey team to the area, and they will make their own, our own contour map covering the project area, because it is important, because these contour maps may have been developed some 20 years back, right, 20 years back, and by now the surface conditions may have changed due to landslides, maybe due to erosion, maybe due to human activities. So, the things may have changed. Therefore, in order to implement the project, normally the project team will mobilize a survey group who will do a fresh contour map covering the area that we are interested in. That is in the final stage, and that will be once the investment decision is taken, because that will cost money. So, we will do all these costly things once the investment decisions are taken. Until investment decisions are taken, we will do the pre-feasibility and other studies using the available plans, that is 1 to 50,000 plans usually available. You can pay a nominal fee and buy or download from the survey department. There are map shops where you can buy them from. And here is a contour map prepared for Sri Lanka by the survey department of Sri Lanka, right. So, they have this grid. So, for each of these grid cells, they have one map. This is 1 to 50,000 map grid, right. So, so each sheet has a number. I do not have the number here, say this they might say this is 61. So, I can go to the map shop and say I want to buy sheet number 61, because my project is somewhere here, I have identified. Therefore, I will buy the sheet number 61. So, maybe I can pay maybe $5 and buy a map, not that expensive, right. So, and also they have each cell point, they have expanded into 1 to 10,000 maps. So, it has therefore 5, right, 5, right, 5 into 5 maps, right. 25 1 to 10,000 maps prepared for each 1 to 50,000 map, right. So, even that is available, but that you can buy if you are really doing a project, identifying the final location where your project components are coming, right. So, you will not know the exact locations, therefore, you can't buy the 1 to 10,000 maps, you then otherwise you have to buy an entire large bundle of 1 to 10,000 maps, which will be useless. First we plan with the 1 to 50,000 map, and then we will try to buy the 1 to 10,000 maps. So, develop our own contour map depending upon the requirement. You can see even the covering the sea area, there are contour maps. So, not only hydropower projects, you are doing any kind of projects, even solar project or whatever, using a large area, like say if you do a 100 megawatt solar project, you will need about 500 acres. So, to know the topography, location, other features, it is always useful to buy a contour map and to mobilize into an area. Even if you are doing an agricultural project using a large extent of land, it is good to buy the contour map in that area, then to identify the land features, rivers available, and then the hills and other things, all the information will be available in the map. So, the contour maps are not only for hydropower development, they are for any activity you are doing as engineers. If you are mobilized into any area to do projects, it is always good to get the contour map of that location and to use them. So, this is a 1 to 50,000 map, you can see the features here. I will zoom it a little bit. You can see lot of features are you can see from a contour map. Here you can see the red color main roads, and then the blue the rivers, right, and reservoirs, all the features are here, right. Green patches may be paddy fields, may be the location of other vegetation, and you can see here is a rocky area, no vegetation, and you can see even the contours are available here, that means it is a hill like rock, right. So, this is a contour map, 1 to 50,000 contour map, right. So, we will go and see a specific area of this map, so that we can be more familiar with the contour map setup. And you know, as a hydropower engineer, your eye must be used to contour maps, right. This is good for any engineer. You should be able to identify the land profile when you are doing any project in anywhere, right. So, the contour maps is a cheap option where you can identify the land profile, land features, etc. So, as engineers we should be able to read contour maps if you are really going to the field, right. So, I have used them in my life for different projects, like even for a large say solar projects. When we want to buy land, we first see whether the land is agreeable before buying the land. For that we will inspect several lands and look at the contour maps, their closeness to highways or the main roads, right. So, if you buy a land somewhere here, it will be much away from main road. So, if you are doing a large project, you will have to build your own roads unless there are existing roads available. So, depending upon the type of the project you are doing, if you have to do a heavy equipment transportation for your project, better to find the land somewhere it is closer to the main roads. Otherwise, you will have to build expensive roads. I am talking about any project, right. Therefore, the contour maps provide such information as we need for any project development, and they are a must for hydropower or small hydropower development. Here I have extracted a certain portion of that map, right, certain portion of that map. You can see here marked 900 here, right. Contour maps do not carry the numbers everywhere. So, you have to have some effort and find out. So, therefore, this hard line, hard color brown line is 900 meters above mean sea level height, and then you can see there is another brown line here. So, if I go along that, you can see it is 800 meters, that above mean sea level. So, in between, therefore, there is a 100 meter level difference, right. There is a 100 meter level difference between them, and in between you can see there are 4 lines or 5 sections, 1, 2, sorry, I will take the pen. Here you can see this is 800, this is 900. So, there is 1, 2, 3, 4 and 5 sections. Therefore, each section has a height of 20 meters. Each section has a height of 20 meters. Therefore, these light lines in between there is a height difference of 20 meters. 20 meters, right. So, 800, 820, 840, 860, 880, 900, right. So, you can identify that there is a uphill here, you will have to climb uphill, and then it goes to further, you can see that I can't see the number, and then this brown line must be 1000 meters. In between there are 4 lines or 5 sections, 20 meter each. So, you can see it is again going uphill, right, uphill, right. And then you can see there is a river flowing here, you can see this is the same line 800, this is 800 meters, right. And then if you take another line below that, so this must be 700, this line, right, in between 800 and 700. So, it is going here 700, and now we can see strangely between this river point and this river point, how much is the height difference? There is a 100 meter height difference, and the water is flowing, you can see this way from high altitude to the low altitude, right. So, we can see between this point and this point, if you want, we can put up a hydropower plant with a 100 meter head, right. That is how we identify hydropower opportunities. But if you go further down, there is another line here which must be below 700 by 20 meter. Here is another line, this may be 680, this may be 660 and so on. I am just not putting the exact numbers, you can find out later, but I just put some tentative values. But from the important point is, from contour maps we can identify where hydropower plants can be developed, where the hydropower opportunities are available, where the height difference are available with water flow, right. So, you may have never been to this site, right. We have done some projects in Uganda, in Sri Lanka. We have invested in I worked in some company called Windforce Private Limited. We invested in 2 hydropower projects in Uganda. So, we did not know anything about that land. So, we got hold of contour maps first, and without ever visiting the site, looked at opportunities and identified, right. But now we have implemented a 8 megawatt project and it is in operation, right. So, that is how you start the project. So, even in India you can identify potential sites and then see whether there is already a power plant constructed. You can go to Google Map and go to the site and see whether it is already there is a power plant. If there is no power plant, you can propose, all these you can do in office without going with the new technology. But the real power plant development you will do later by visiting the site, etc., right. So, you can see that there is a road here, the main road, right. You can see the kilometer marks are also there, 164, 63, 62 and so on. So, you can know the distances, all these things, and there are, you can see this white color, this is a by road, this is a by road going from this one, you can see. And then there are this is a higher grade road, not red light, this may be B grade, this white one may be C grade roads. So, you can identify what are the roads available near your project. If you identify this as a project location, it is good that you have a B grade road close by, right. Then you can go, if you want to make a site visit, you can go along this road and park your vehicle here and then have a walk here, right. So, your site visits all you can plan, right, with the help of contour maps. Therefore, contour maps are helpful in numerous ways in developing hydropower plants. And we can see a this black color broken line, that must be a provincial boundary, that must be a provincial boundary, right. And so there are many other, right, many other information available, and there are small rivers, you can see this hairline like small rivers, right, they are coming and joining the main river, right. And also remember, rivers flow, when the rivers flow, contours are like this. So, the river flow is this direction, right. So, when you stand along the river looking at the flowing water, your hands like contours will be like this, the hands like in this way. So, you can easily identify which way the rivers are flowing. So, this is flowing this way therefore, otherwise sometimes you get confused which way the rivers are flowing, this way, because the contours are like this, right, and same way you can identify. We will look at these things in details in later topics. This is just to get familiar. Here I have marked a possible way of identifying the river location. So, you can see in this particular river there are contour lines like this, you can see, and their heights are marked. So, I have selected to tap water here, diversion weir, right, and then take water along this canal to a location here where the 4 bay tank is located, right. I told in the previous discussion that normally the contour has canal has a very low slope. So, normally about 1 to 1000 as I said earlier, but exact amount you can calculate using a different formula, but roughly about 1 to 1000. So, that means you go almost parallel to a contour line, right, almost parallel to a contour line, because contour lines are lines of equal height. So, you need only 1 to 1000, that is 1 meter drop for every 1 kilometer. Therefore, you will pan your canal very parallel to contour lines, right, and then come to a convenient location, and then your penstock should come cutting many contours, because that is where the slope is. When contours are cut, between every contour 2 lines there is a 20 meter drop, 20 meter height difference. Therefore, your penstock should come cutting many contour lines in a short distance. That is where your head, your water flow pressure comes in. We want to keep the penstock as short as possible, right. So, that is the idea. So, I have put the powerhouse here. This is typically how you plan a hydropower plant using a contour map. Identify a contour location, basically how to develop a hydropower plant. Then there is a concept of how much water can come into this diversion point. That is a good question. So, that depends upon the rain upstream. Then all the rain will not come to it, it come to certain lands above this point which are sloping into the river can collect water into this. So, this gives the idea of catchment area. So, this is called the catchment area. When you have a catchment area, you have to identify the catchment boundaries, that is which area has the potential of water that coming in the rain can have a chance of flowing into my diversion point, right. So, I have marked here the catchment boundary, this is the catchment boundary, right. How to mark it I will discuss in a later topic, right. So, water in this area falling in this area can come to it, but water coming here will not come into our catchment. It will go to this small river and water will go to some other part, that will not come into our river, our diversion point. Therefore, it is important to identify what is your catchment area. If it is a small catchment area, maybe you will not have enough water in the long run. So, a project therefore must have suitable amount of say area as catchment area. Typically, for a high head project like 200 meter head project, catchment area will be 10, 15, 20 square kilometers. But if it is a low head project like say 20 meter, 30 meter head, maybe catchment area may be 200 square kilometers, depending upon that. We will discuss these things a little bit in detail later on. Okay. Now, we will go to the second part of this lecture, right, that is identification of hydropower development opportunities and locating the diversion weir for a given project. So, with this background knowledge that we have already acquired, let us see how to do it in a more precise way when there are number of opportunities, which one is better and how to decide on that, right. So, as we said earlier, this is a typical layout that we have been looking at of developing a run of river type small hydropower plant, right, run of river type small hydropower plant. So, now the components we are little familiar. We have a diversion point, or we call it diversion point, intake or weir, or there are a number of words that we are using. Here is another new term that we didn't discuss earlier, settling basin. Settling basin, we will discuss about settling basin in a little more detail in a subsequent topic, but settling basins are required because from rivers we get silt and sand. Silt and sand flows in rivers, amount depends upon the type of the river, right. So, silt and sand, when it comes, if the silt goes into the or the sand goes into the penstock, what will happen? It will go and damage the turbine, right. It will go and erode the turbine, and thereby turbine will be destroyed. Therefore, we want silt to be taken out of the canal or the tunnel or whatever we are using before the water enters the penstock. So, for that we are using a settling basin, or sometimes we call it desilting tank, desilting basin or desilting tank, right. We will have number of them, maybe at the initially if the river carries lot of sand. If the river water is always brownish, that means it carries sand and silt, right. So, we will have one at the intake and remove silt as much as possible entering it. But we will have, if the canal is long, say 1 kilometer long, then we will have another in between, and we must have one here at the forebay tank. A desilting basin at the forebay tank is a must, because something can fall in here from top, and then it can be carried to the penstock. Therefore, we will have number of desilting basins right upstream depending upon the length of the canal, but we must have a desilting basin right at the forebay tank, enter to the forebay tank, to avoid the possibility of any sand going and entering the penstock, right. Why then, somebody might ask, why we spend desilting basins at the upper side? We can have one final desilting basin here rather than spending money and having desilting basins in the middle and up. What happens is, when silt enters here, it gets deposited in the bottom of the canal, because the canal flow rate is not very high, it is a very slow slope. Therefore, over the time silt fills, right, and then the canal height shortens, then the water cannot flow now, right. Therefore, it is important no silt accumulate in the canal. That is why in long canals we need couple of desilting tanks in between also, that depends upon the river condition, the silt level, etc. Therefore, normally when we go for the first inspection, we will take couple of water samples and see how much silt is there, especially in the flood season, and thereby plan accordingly the desilting basins, required number of them, because they are having a certain cost, but we will try to minimize the cost as well as minimize the possibility of salt depositing. Here I have selected another contour map. This is slightly different from previous one. This is from another country. This is 1 to 63,360, but that survey department has selected this, right. So, it does not matter the type of curve, whatever the one that you get, we can use. It is a matter of the height difference and the details available, etc. So, this is a little expanded one I have selected. We can see contour heights are given in these are all in meters, right. You can see here it is 200 meter, 200, 250, 300. So, you can see between these numbers there is one line here. So, therefore, it must be 300 and 350. So, this must be 325, right. So, now in this particular map between any two lines height difference is how much? 25 meters. So, it is a different scale used by a different survey authority, right. So, you will encounter many such small differences. The previous one, the height difference was 20 meters and here it is 25 meters. So, about the details it will be different, and when you do your own contour map for the site using a survey team, you can ask him, I want 10 meter height difference, or I want 5 meter height difference for my scale, because in order to plan your civil device, civil components, you might need that detail, right. So, we can see, so this particular map, and we can see that some river system here, this it is not blue in this particular one, these are rivers, and there is another branch also coming and joining, and there is another river system here. Branches coming and joining, right, river system. So, and these both river systems come and join at this point B and make a larger river, right. Now, this is given to a hydropower engineer like you, right. Now, you are going to be a hydropower engineer. So, given a hydropower engineer by your company and said, okay, see whether we can develop a hydropower plant, or whether there are a number of options, so one option or whatever, you are asked to look at this and give your opinion, right. So, now you look at, so then when you look at, you can see, because we know for hydropower, I will come to this formula later, but for the for your benefit I will mention the power, we will discuss this later on. Power developed from a hydropower plant is equal to efficiency into Q rho G H. Rho and G we know, rho is density, G is gravitational constant, we are familiar with. Q is the flow rate, H is the height difference, or what you call the head, right. Q is flow rate in cubic meters per second, H is in meters the water head height difference between your diversion weir and the forebay tank level and your turbine level, right. So, that is what we are interested in hydropower, what is the height, potential energy is in the height. So, we want to convert that to, so you can see it is the power is, this is in watts or kilowatts, right. It is directly proportional to Q and H, flow rate and head, right, flow rate and head. Now, with this in mind, now the hydropower engineer looks at this. So, he first looks at the river system, this river system, what you have marked as A, he look at this, and then he thinks, okay, I will get tap water here at point A using this river system, right, and take it parallel to a contour line, this is his canal, right, and take it to point A1 using a canal. So, here will be the forebay tank, right, forebay tank that we looked at earlier, right, and then I will have my penstock from A1 to C. C is near the river, little above the sea, so that the flood level is not exceeded, and at C we have the power plant, and that is the hydropower scheme. And we can see B1 is at 275 level, A1 is at 350 level, A1 is at 350 level, C is at 200. So, that power plant has a head of 150 meters, right. So, that is a project, right. So, whatever the water come into this play QA will be available for power generation. So, his power plant will have a output of, power plant A will have output of efficiency into QA rho G into H, H is 150 meters. Q will depend, Q you can't put a value, it will depend upon the rain conditions and the water available upstream, the flow of that day, right. So, Q is a variable, therefore, it is not a constant value. Q will go up and down depending upon the time of the year, time of the day, right, depending upon the water availability in the river, right. And then your colleague suggests, you are looking in a team, your team is looking at this diagram now, your colleague suggests, wait, if we go to point B, we can increase our Q. Why? Another river comes and joins us, right. Another river system comes and joins us at B, this river. So, our Q will be therefore naturally larger, but of course, we will lose some head because it is at a lower height, right. Therefore, he suggests shall we look at this option also. He suggests we tap water at B, take water along this canal to B1, which is at 275 contour height, and then locate the power plant at the same place C at 200. But now, our power plant has a head of 75 meters only, 75 meters only, but Q at B will be larger than Q at A, right, Q at A. So, there are two options now. From the same map we have extracted now two information, right. Then which is better, that we have to decide on economic terms, which project will bring better financial returns will be the project to be selected, right. That we have to design the project, we have to look at the two projects compared and do a cash flow analysis and to see which project is financially more attractive. That is how we take the decisions in the field. So, here is a summary of the two projects, right. So, in option 1, diversion weir is at A, canal path A to A1, right, canal path A to A1 and penstock A1 to C, powerhouse at C, right, powerhouse at C, head is 150 meters. Same way, if we have the point B as your diversion location, B to B1 as the canal, B1 for bay tank, penstock B1 to C, power plant at C and head of 75 meters. But now, this option 2 will have a higher flow, because two rivers have joined together, right. So, I have summarized them here, I do not want to read it again. You can see final line I will read, decision will be based on better economic returns. So, you do it and your financial controller or financial accounting department, they will do a cash flow analysis after you do the preliminary pre-feasibility and estimate approximate costs, and approximately how much energy you can generate. Those things we are going to discuss in the future topics, how many gigawatt hours or how many million kilowatt hours you can produce every year. That is important, because that is what you can sell, right. And then your plant will have a certain cost, your diversion weir or dam will cost, your canal will cost, your 4-bay tank will cost, your penstock will cost, your powerhouse will cost, your turbines and generators and the other electrical equipment will cost. If you have a step up transformer, that will have a cost, and if you have an interconnecting line, transmission line, that will have a cost. So, you can add them up together, that will be your total project cost, right. So, total project cost versus amount of millions of kilowatt hours you can estimate to be generated every year, that is you can sell. Then you can do a cost benefit analysis and see whether plant A or plant B is the better option. That is how when you do the things in the field. But we in this particular course we will not discuss about cash flow analysis and other things because of the time limitations, but you can use an accountant or a financial analyst to do those comparisons. So, you can see now here, now once you have interested in this, you need to know, right. Now, your boss will ask you, now you have looked at these options, now you are telling there are two options. What is the capacity of these two options? How many kilowatt or how many megawatts each plant is sizing? And now you have not been to the site, you do not have flow data, but your boss is asking how many megawatts each project. So, you can't say I do not know, right. So, you can make a best estimation from this, right. Still in the office, maybe this location may be some other country, right. Now, you have to answer your boss question, how much is the megawatt capacity for project A and project B, right. Very difficult of course, but you have to give a positive answer, right. Then you get hold of other information. Now, you have to know how much water will come to point A for my diversion, how much will come to point B, right, we have to know. Then you can at least have an average idea how much water comes, then you can divide by the number of seconds in the year and say per second this much can be expected. But for that you must know how much water is coming to your diversion point. How much water that will come to your diversion point depends upon how much water will come into your catchment area, and therefore, it depends upon rainfall as well as the catchment area. If the catchment area is large, rainfall is large, you can expect more water. If the catchment is small, less water. So, therefore, you need to mark the catchment area in this map. So, let us see how it is done. You can see point A, the catchment is marked by this line, you can see. That is the catchment for project A. Now, see how it has been marked, right. You can see water flow, I said contours are like this, right, contours are like this, right. But you can see this is a hill range, this is a hill range, you can see this is a hill top, this is 500 meters, you can see 400, this is 500 meters, this is also 500 meters. Therefore, you can see we have made a fictitious line here that divides the hill range, this way another slope, this way one slope, right. And here also you can see there is a hill tops, and water into this river system goes from here to there. If the rain falls here, that water goes into this river system. If the water falls here, water goes into this river system. And also incidentally we note that in contour boundaries, contours are in the other direction compared to the contour shape in the river, right. Here also you can see. So, you can use this all these knowledge in marking the contours, the contour catchment area boundaries, rivers this way, contours this way, and other hilltops you have to approximately guess, but the criteria is you judge whether rainwater falling at that location, whether that can come into your river system of interest or whether it can go to the other river system. Here we are looking at the project A, therefore, we are looking at this catchment area. So, if the water falls here, we know that cannot come into our system. So, that goes to this river system, therefore, that cannot be our catchment area, right. So, always argue whether the water falling there, rainwater falling there can come into your catchment area or not. If it cannot come, that part cannot be your catchment area, right. So, this is initially difficult, but when you are accustomed to, you can gradually learn, right, how to mark the catchment area. So, once you mark the catchment area, right, if you know the rainfall in this area, say annual average rainfall is 1000 millimeters, then you know annually how much water is coming into your catchment area. Suppose your catchment area is 20 square kilometers, catchment area is found to be 20 square kilometers and the rain is 1000 millimeters, so 1 meter. Therefore, your catchment has a water reception of 20 kilometer squared is 10 to the power 6 meter squares, right, into 1 meter, that is 20 into 10 to the power 6 cubic meters are coming into your catchment, right. I am just putting random numbers here, right, just to understand the principle. So, we are sure that we can get on average about 20 million cubic meters into your catchment area, but there is no guarantee that this will go into my diversion point, because in between lot of things happen. Some water will be evaporated, some water will be soaked into the soil, some water will be taken by the trees, right, and so on. So, only a portion of that can come into my diversion point, right. Let us look at some more slides describing this. Here you can say rainfall map, you can from this you can for any country there is a weather stations marked. So, you can get the rainfall data from the closest weather station to your site, that is one way, right. And also there are maps like this, rainfall map for Indian city states also there must be. You can see on a scale it says on average how much rain can be expected. You can see in Sri Lanka there are very wet areas, this you can see here you can expect about 5000 millimeters per annum, right, water. But there are some dry areas, you can see very dry areas, this is less than, right, 1000 millimeters, right. So, you can see. So, with this kind of map if your location is somewhere here, if your project is located somewhere here, catchment area is here, you can approximately get, it may be 2000 to 2500, you can approximately 2250, because we are doing an initial estimation, because your boss is asking the question, right, how many megawatts. So, you are trying to find a solution on a reasonable scientific based solution, right, because we are doing an initial investigation. We can go to the site, get river measurements and all these things at a later stage, but this is an initial look, right, initial look. So, once you know this, you can calculate, as I said earlier, this one. But there are, if you are lucky, rather than using these maps will be very approximate, these maps will be very approximate. But if you are lucky, you can give a call to these weather stations and check where is the nearest rain gauge to this site. You give the coordinates of your site and ask them where is the closest rain gauges, where are the closest rain gauges to this site, right. And then they will say there is one at 10 kilometers away, another at 25 kilometers away, another at 50 kilometers away. At these locations they might say 1 or 2 or 3 or 4 rain gauges close by to your catchment area. Then you can get the average of that, right. You can call them and get the annual rainfall and get the average of those 4 rain gauges, rather than going by this approximation, because these are very rough, but actual measurements will be much better, right, actual measurements will be much better. Therefore, so this is the worst case, we use this, but if you are lucky we can find close by rain gauges. So, I have here marked, you can see for project B, for example, for project B I have marked the catchment area. You can see the project B is this one. So, the catchment area is like this. It includes project A also, because the water in project A also come into it, right. So, this area I have separately drawn here, traced it to a separate diagram here, same catchment area. So, project B is somewhere here, diversion point is somewhere here, right, B, right. So, I want to know the areas now. So, I have got the area, and the weather stations told me there is a rain gauge here W1, they told me there is a rain gauge here W3 and a W2 rain gauge here. Now, one way is getting the average of them, but they are at different distances. So, it is not very reasonable. Therefore, what I have done is I have marked a triangle here, because there are 3 weather stations, weather station 1, weather station 3, 2. I have marked a triangle here and then bisected the sides, bisected the site. Now, I can divide my catchment area into 3 areas. I can mark this portion of the catchment area is more represented by W3, it is closer to that, and this segment of the catchment area is more represented by W1 weather station, and this area is more represented by W2, because these areas are pretty large, remember maybe 100 square kilometers, right, 100 square kilometers. So, therefore, now I have got a good estimation. Now, I can calculate what is the area here. area calculation of a catchment area is not difficult. Even if you go to Google map and give the boundary, it will calculate the area for you. There are softwares you can use for catchment area calculation, you just have to give the boundary, right, when the boundary is given. So, when you give this boundary, there are calculators, you can calculate how many square kilometers. Now, I have got the information, right, I have got the information. This line is wrong, this line should come here, right. I have got the information, right, that you know at weather station 1 rainfall is W1 meters per year. Here the rain gauge weather station 2, it is let us say W2 meters per year. Here W3 meters per year, that is the average annual rainfall, right. So, I have got that information, and therefore, I will say my average rainfall is, right, average rainfall for my entire catchment I can calculate. For example, this is one way of doing it. Average rainfall is, right, water will come this area is AW1, I have put square meters, right. So, AW1 into W1 plus area W2 into rainfall in W2 plus area W3 into rainfall W3 divided by the total area, W3, right, which will give me average rainfall that can be expected in the total area, total catchment area, because I got 3 rain gauges. If I got 2 rain gauges, I can just bisect it and get it 2 areas, right. If I get only 1, I can use that. Since I have got 3, I have put that sample here. So, I have put here some typical numbers. W1 is 2500 millimeters. So, I have put them in millimeters, W2 3200 millimeters, W3 1800 millimeters. Area WK1, sorry, area in the AW1 3 square kilometers, AW2 12 square kilometers, AW3 8 square kilometers. So, now you can get the average rainfall, right, rainfall into area, rainfall into area, rainfall into area divided by the total area, 2621 millimeters, right. So, that is in my catchment area, average rainfall is 2621 millimeters as per the 3 weather stations that are available, right. So, I can depend upon this number to some extent, right. Now, I told you that all the rain that goes into this will not come into my diversion point. Why? Because the water will be evaporated, trees will transpirate it, trees will absorb and leaves will transpirate it to the air, and some water will go to the groundwater, right. Some water will be utilized by the people, animals and so on. So, only portion of it can come to my diversion point, Therefore, you know that people have developed a graph like this, rainfall runoff graphs, right, rainfall runoff graph. So, you can see the vertical axis is rainfall, horizontal axis runoff. What does it mean? If the rainfall is so much, how come much will go in the river? Now, for example, here, right, if the rainfall is here, let us say this is 1750, runoff is 0 almost. What does it mean? If the rainfall, annual average rainfall is this low, river will be dry almost, right. But if the average rainfall is say 3500 millimeters, then your river will carry approximately say 2300, corresponding to 2300 millimeters of rainfall will be flowing in the river. And this previous calculation showed us our catchment has the average rainfall of 2621. So, I have marked it here 2621 and corresponding runoff is 1200 millimeters, 1200 millimeters, right. Therefore, now I can calculate how much water comes into my catchment, right. My catchment now corresponding to 2600 millimeters rainfall is 1200 and my total area of the catchment is AW1 plus AW2 plus AW3, which happens to be 3 plus 12 plus 8, that is 23 square kilometers, right. Now, I know water volume coming into my diversion point, right. Water volume coming into my diversion point is catchment area A into rainfall. This is the water volume at diversion point, right. So, that is in this case 23 square kilometers, I will convert it to meter squared by multiplying by 6 square meters. Rainfall is now 1200 millimeters of 1.2 meters. So, now this will convert to be the amount of cubic meters of water is coming to my diversion point that can be taken in for my power plant use, right. Of course, you will have to minimum flow a little bit you have to reduce, but let us forget there is no minimum flow. Therefore, now we can calculate, right. So, it is 1200 millimeters into 23 kilometers squared. Now, I divided by the number of seconds in the year, 365 days, 24 hours, 3600 seconds, right. So, when you multiply all these things with cubic meters and seconds, you can get average flow rate as, right, 0.875 square cubic meters per second. Now, we have a Q value, right. P we know efficiency into Q rho G H, right. H for the project B is 75 meters. Now, we can put this value efficiency into Q is 0.875, rho is 1000 kilograms per cubic meter, G is 9.81, H is 75, right. So, we can now calculate the project capacity, right. Efficiency normally total efficiency for the project we will see later on how it can be calculated about 75%, right. So, you can put something like 0.75. Now, you can see you come with the project like 552 kilowatts project B, right. So, with these numbers I have put some random numbers for areas and rainfall etc., but exact numbers you will get when you are doing a real project, right. So, you can now tell your boss one project is having 550 kilowatts. Same way you can do it for the project A, right, and say project A has a capacity of this much, right, and then now you have answers, right. But this is very approximate, remember, which you can do when you are doing initial investigations from your office with available theoretical knowledge. It does not cost you anything other than your working hours, number of working hours. But if it happens to be 50 kilowatt, then you will say there is no project, we will forget about it, right. It is a very small, no point company doing a 50 kilowatt project, right. But it since 500 kilowatt, it definitely there is a project. So, the first further investigations are worth doing, right, further investigations worth doing. So, this is how you initially identify project locations using a contour map, right, project locations using a contour map, right. So, it may be in some other country, it may be in some other state, right, you have never visited, but using the available literature, available data, you can do an initial investigation and see whether there is a project where it is worthwhile to do further investigations, right. So, in this lecture we have discussed about our initial concept of small hydropower compared to large hydropower, what are the advantages of small hydropower, and also initial concept of using contour maps for project identification. And we said that what there will be a water diversification. Usually small hydropower plants don't have tunnels. Instead we use a low pressure canal or channel to bring water to a closer location, so that we can keep the penstock length shorter and the penstock cost lower, and then develop the project in an economical way. And also we looked at how we can do initial investigation of a project location, whether there is a sufficient capacity, initial estimation of a sufficient capacity. And with this we can go further and make further investigations and develop the project, which will be discussing in future modules of this course. If there are any questions, we can take up now, or otherwise I will give when I have extra time, I will give some other time slot, common time slot, where we can discuss about further questions you may have. If there is an immediate question from online participants or from you, I can take it and spend a few minutes. Otherwise we will do it in a common slot where you can study it further and come prepared for clarifications of your own after your own studies, because sometimes this may be completely new to you. Therefore you will need some time to digest the concepts and to understand yourself, and then develop the necessary knowledge and tools and other things for developing your skills in developing hydropower. So I studied these things in late 1990s when my company, so I worked for a joint venture company between Norway and Sri Lanka as a general manager and the project manager also. That was funded by Fund of Norway and another company of Trondheim Energy Work. They were the foreign shareholders, and in Sri Lanka it was Lanka Transformers Limited and another Sri Lankan company. So they jointly invested in these projects, and so we developed two projects, a 4 megawatt project and a 2.5 megawatt projects in two different locations. So I studied them separate, I studied, and my other engineers, we teamed up, civil, electrical, mechanical engineers teamed up, and under my guidance we did these projects, and still they are in operation. They were commissioned in 2003 and 2004. Now over 20 years they are in operation and no issues. We bought machines for the first plant from Germany and the second plant from India, and from that gentleman I was showing you, Kerala Investigations, he was the one, the company is weir near Delhi. So we purchased for the 4 megawatt plant machines from them, and for the 2.5 megawatt plant we bought from a company called Folk Wasserkraft WKV, a German company. And both machines are good because weir also in India they produce under German license. Original company is German, but under their license they produce equipment. And I think in India there are many small hydropower turbine manufacturers. So I think we will conclude there, and there is another session maybe in the afternoon, we will meet up there. Rho, yes, yeah. The question is what is rho? Rho is the density of water, but this equation we will discuss later how to obtain this. Q rho GH, this is hydropower equation for large or small hydropower. In a future module we will discuss how to derive that equation, right? Mathematically how to derive it we will discuss later in some other slide, some other module, right, under the same course, right? You will encounter it later. So we will conclude there for today, right? Okay, thank you, and see you in some other module. Okay.